Question? This reaction will also be done without solvent. Did we do one inorganic one without solvent? Maybe not. Maybe not. But it's going to be done grinding. Okay. It does take a little elbow grease. Y'all know what elbow grease is? Okay. You can't just kind of grind and then whatever. You got to grind it hard for the entire time. That's one reason it's team, because somebody can grind for a couple of minutes and then you take a break and let the other team members grind. Other questions before we get started?
How many people are in your group?
Probably 3 to 4. Probably 4 would be good to shoot for. I'd rather not have 5 unless there's just an odd man out or something. You want to choose your own groups, or you want to pull groups out of a hat or something? Do what? Choose your own? Okay, y'all can do that. Next time we'll pull names out of a hat. Big. Document camera. Okay, so while this is, for some reason it's already one done. Imines. We did mechanism, enamine. That's an ene with an amine. What do you call an ene with an alcohol? Enol. An enol. We'll see enols a little bit later also, right? Enol, enamine. There's special type of imines. Your hydrazones made using hydrazine, and your oximes made using hydroxylamine. Those are the special type of imines. We also have a chemical test here with imines. And this is where we'll pick up. The 2,4-DNP test. We've seen chemical tests before. For example, Tollin's test. What others did we see? Jones oxidation test. Was there one more? Lucas. Okay. This is the 4th one we've seen, DNP. It's a test for aldehydes or ketones. We're doing chemistry of aldehydes and ketones right now, right? Okay. If you have an unknown, you can treat it with 2,4-dinitrophenylhydrazine. If it's an aldehyde or ketone, this amine on the end will react with the carbonyl. You'll lose water. You'll make the imine. Since there's a nitrogen bonded there, we call this a hydrazone. It's a 2,4-dinitrophenylhydrazone. Well, 2,4-DNP hydrazones are typically always solids. They're yellow or orange. And it will also precipitate very readily. Pretty insoluble with these nitro groups. The idea is that this is usually a liquid or in solution. Okay? You maybe dissolve it in ethanol or something. You add in your 2,4-DNP, your hydrazine, which is a liquid or usually in solution. It's actually a liquid. As soon as you add it in, if you get a precipitate, it's 99%, it means that this is the precipitate. You're only going to get a precipitate if it's an aldehyde or ketone. If it's, say, ester, you will not get a precipitate. Acid derivatives don't produce imines. An acid derivative would do an additional elimination. It would have like a leaving group, and you would get like an amine. Okay, that would be a leaving group chemistry. Okay, you only get a precipitate when it's an aldehyde or ketone. So in the end, if you get the precipitate, it's usually, nothing is 100% anywhere. But it typically means you have an aldehyde or ketone. Now, of course, Why would you need to use this? Well, if you have an unknown and you're saying, well, I'm not sure if it's a ketone or an ester. The IR shows carbonyl. Well, yeah, both would show carbonyl. NMR, for some reason, I just can't tell. Well, what could you do? Well, do a 2,4-DNP test. If you get a precipitate, which one do you have? It supports ketone. Okay? Now, either ketone or aldehyde will give that. Now, how can you distinguish between ketone and aldehyde? Because this won't. This gives positive tests for both. But what would distinguish these two? What chemical test? Well, that's possible, but in terms of chemical test, wet chemical test. Now, Jones is for alcohols. Although, hold on. Traditionally, Jones is for alcohols, but aldehydes can be oxidized, so Jones could give you a color change. Yes. I was going to say Tollens, though. Tollens is for aldehydes. You could then do a Tollens test. What if DNP was positive but Tollens was negative?
Ketone.
The ketone. If they're both positive, that means it's an aldehyde. Okay? So basically we have another test here, and the visual positive is a precipitate bed. Okay. Next, Wolff-Kishner reduction. We saw this when we were doing aromatic chemistry. For example, you can do a Friedel-Crafts acylation and put this ketone on. Then you can remove the oxygen to give the propyl group. Basically, we're putting two H's here. Okay? We did this 3 different ways. The most traditional textbook way is the zinc mercury amalgam with HCl. What's that called? That's got a name. Clemenson reduction, yeah, that's the textbook way. We also said you could do it with hydrogen and like palladium on carbon or something. Usually you don't see that in textbook too often. And usually the carbonyl has to be next to an aromatic. Wolff-Kishner is almost as common as the Clemenson reduction. We did not show mechanism during test 2. What's the mechanism here? For a long time, people didn't know the mechanism. They still used the reaction. It's like a drug. You don't have to know how the drug acts, how the drug cures cancer. But if it does, you're going to use it, right? To get a drug approved, it has to be safe and effective. You don't have to know how it acts. I mean, they used this reaction a good bit. Eventually, though, a mechanism was proposed. Importantly, when you're trying to come up with a mechanism, it's good to know what all is formed. This is the major organic product. What else is formed here if we completely balance this? Water. Actually, yes, water is good. Plus what? Okay, on that side you have some nitrogens. On this side, what's going to be nitrogen? In the form of what? It's actually N2. Okay, you form N2 gas, nitrogen gas. That may be completely everything there. We need what? It's not balanced. I'm just saying in terms of the constituents that are started and produced. You can balance it if you like. I'm not good at balancing equations. This is just saying it does form water, it does form nitrogen, but molar equivalency, I'm not saying that. Does it form anything else? Well, we got a potassium over here. What's the potassium over there? It can't just disappear.
How reform?
Yeah, there's 2 hydrogen.
So, do you think it forms KH?
Now KOH reformed.
I think we're going to end up with KOH over here. Thus, KOH seems to be a what? Ah, yeah. We can see if that's indeed it when we propose a mechanism, if we regenerate KOH. Otherwise, the K plus is going to have to sit with something. There's no Cl minus it can sit with, or, you know. Or maybe we make K NH2. You know? We'll see. Okay, the first step of this mechanism is to make the imine. I'm just going to say phenyl, double bond N, and that's got an NH2. Okay? Did we do this up top? Yeah, the hydrazone. Hydrazone is the first thing you get. And we did that up above. You don't have to have an acid catalyst. And indeed, there is no acid catalyst here. We're under basic conditions. Okay? Plus what? Plus water. There's your generation of water, which we showed over there, right? Whenever you make your imine or your acetal, you generate water. That's the fate of the oxygen from the carbonyl. Okay? So, you already know that mechanism. How do we then go from here to final product? Well, it's actually pretty straightforward. It's very unique, but mechanistically it's pretty straightforward. We got a base. What do bases do? They abstract H's. Okay? Let's see. We've got to make nitrogen. We know that because somebody along the way said, hey, look, nitrogen gas is formed. And there's ways you can tell that. So balloon over your reaction as it progresses, the balloon starts inflating. And then you can, from there, you can maybe do a GC of what's in there, and you can see nitrogen or a variety of ways. But these nitrogens don't have H's, right? So do you agree that we got to get them off of that nitrogen?
Yes.
What might take them off? The hydroxide, which takes H's. Okay? Where do we need to put H's on them? This carbon, it's got two. So you got to assess sort of what's going on. But after that, I would encourage you to then focus back over here with, okay, what's step one? Don't try to just get there automatically. You got to do one step at a time. What do you want to do first?
Take an H.
Yes, I would take an H. Let's draw these out so when we take them, we can show our electron movement. Hydroxide takes this H, leaves these behind, right? What do we get? There's one left. There's two lone pairs now because there was one to begin with. That's a minus charge. Plus what? Plus a second water. Okay? Is this reasonable? Can we make this anion?
Yes.
What type of stability does this anion have? It's electronegative heteroatom. Now it's not as electronegative as chlorine or oxygen, but it's still electronegative nitrogen. Not only is it electronegative, what else can we show that is resonance? These electrons can move here, and these electrons can move here. Electrons in, electrons out. And if we do resonance, I'm going to come right here. You've already got water there. We get boom, boom, boom. H there. What's between the nitrogens now?
Double bond.
Double bond, one lone pair left. There's a lone pair of the other one. Single bond here, what's here now?
Negative.
That's a negative. Ah, resonance arrow. Those are just resonance structures, right? Delocalization of the anion. Okay, what do we need to get on these on this carbon? H's. Where can the H's come from? Water. Boom. Boom.
Could you do an H plus transfer?
You mean that H? You actually could, because we're just going to eventually do that. Let's go back to that. I'm going to just get rid of this for now. So now we got an H there. There we go. Plus what? Plus hydroxide. Okay. What do you want to do next? Basically, we're going to repeat the process, except it's going to be a little bit different. Take the H, electrons behind. Boom, boom, boom. There's an H there. I'm going to keep drawing it in. Boom, 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 boom. There's no H, and that's a minus charge. 2, 4, 6, 8. 1, 2, 3, 4, 5. Yeah, minus charge, yeah? Okay, at this point, these electrons come in here and kick this off. And that's going to give, boom, boom, boom. There's an H. What's on this carbon now? Lone pair, that's a minus, plus what? Nitrogen gas. Is this a resonance structure? No, this is not resonance, because, I mean, now we have two different molecules. This is not the same molecule with just pi electrons rearranged. Right? Is this the same molecule as that? No, these are not resonance structures. This is actually, you can call it a leaving group. Is that carbanion a good leaving group? Not really, and up till now I would say never do this. So this is actually something that goes against what we've always kind of said. I've always said that an H and a plain carbon is never going to leave. Okay? Now the Wolff-Kishner actually does require heat, and traditionally, especially early on, until improvements were made, it required like 200, 300 degrees. It required very extreme conditions, probably because of that step right there, kicking off that carbanion. Now, if it's phenyl, this is resonance stabilized into the phenyl. But we know it works even with this is not any resonance here. Okay? So this is a questionable step. At this point, what do we need to do to get the final product? Well, we formed that water right here, right? We got that plus water. Well, now this is strongly basic. It takes the H. What do we get? We get final product. There's two H's there now. Plus what? Plus hydroxide. So indeed, we really did reform the hydroxide at the end in our proposed mechanism. And indeed, hydroxide can just be stated as what? A catalyst. You only need like one molecule of hydroxide, theoretically. So a little questionable step there. My question is, well, first off, we know the reaction takes place. If you don't like this mechanism, does anybody have an alternative suggestion of what the mechanism might be?
H plus transfer.
H plus transfer of where?
I have to separate it.
You'd still essentially do the same thing.
Right here?
Yeah.
Well, you could just do an H, you could just transfer this H to here. That would just give you that structure.
That one.
It would just give you this one directly. And indeed, in many cases before, we just went here directly with an H plus transfer, and I sort of skipped this where it kind of goes to solvent and then it comes back. And who's to say the H doesn't come from there? I mean, but keeping track of that H's are often bouncing around. Okay, anybody have a better mechanism? This is the currently proposed mechanism. You know, I don't know how much this has been, how many additional studies have been done to further prove this. A lot of times when mechanisms are kind of investigated, you do like deuterium instead of H. And you see, does two deuteriums end up here? If you use KOD, you know, you can get KOD, which is just the deuterium isotope of H. Then if you use H's here, well, you can see that may prove, do any of the original H's in hydrazine end up on the carbon? But you can sometimes prove mechanisms using isotopes. Because you can follow your isotopes where they end up. Okay, so this is the Wolff-Kishner. Basically, you make the hydrazone, and then from there, it's just acid-base chemistry. You take the H off, you do resonance, you put it back on somewhere else. But that over there is not resonance because we're splitting the molecule. After you see it, is it kind of straightforward? So that's the Wolff-Kishner. All right. That's right, Mr. Wolff. I'll give $1 to anybody who tells me where that's right, Mr. Wolff comes from. Once, going twice. CSI Miami. Don't you remember he always used to say that's right, Mr. Wolff.
Oh, yeah, that
Gotta watch that, sir. Mr. Wolff was one of the technicians or something, and he would always say that's right, Mr. Wolff. Okay. Good old Wolff-Kishner. Somebody probably 100 years ago tried to make an imine using hydroxide, and they got this product, and they're like, what happened to my nitrogens?
You said that this used to take like 200 degrees until improvements were made.
Yeah, over the years you see publications of improving the Wolff-Kishner. You can use some unique solvents that help speed up the reaction. You know, we never talk about solvents, but solvents can influence reactions a lot. You can also do special things like microwave. So there's some unique things that make it where the Wolff-Kishner is not as harsh. A lot of functional groups can't survive KOH 200 degrees. I mean, it'll just destroy lots of functional groups. If you have a nitrile in your compound, it'll hydrolyze that in a heartbeat. So you look for milder conditions where you get more selectivity, functional group selectivity. Okay, Strecker next. I think it is. Okay, Strecker amino acid synthesis. This is going to be addition of HCN to an imine, and then we're going to hydrolyze the nitrile. I think you're a good chance of seeing this in biochemistry, where you talk about synthesis of amino acids. And usually when you say amino acid, you're usually talking about alpha amino acid, where first carbon is alpha, and the amine is on the alpha carbon. It's alpha amino carboxylic acid. These are your protein building blocks. There's like 20 natural ones, but people make non-natural ones to make unique proteins. It's big in biochemistry. Okay, start with an aldehyde. You react this with KCN ammonium chloride. You can get this here. Now, what's going on here? These reagents may look a little bit complex, but it's nothing but a cyanide source, a proton source and ammonia source. Okay? You could do this like ACN and ammonia. And that may look a little bit more simple. Of course, both of these are gases. Gases are harder to use in lab, where both of these are solids. So, you look at a reagent, you need to boil it down to what are the reacting components. You've got cyanide, you've got sort of an acidic proton, and you've got ammonia. That's what's here. The acidic proton is sitting with the ammonia. Basically, if you also included HCl, this would probably look a little more simple to you. Of course, ammonia and HCl are going to react to form what? Ammonium chloride. And then HCN, you really don't need an additional proton, so that can be Cn minus. If you got a minus, you got to have a plus. So this can be potassium or maybe it's sodium, but that's a spectator ion. Okay? So the components are here. Now ammonium chloride is slightly acidic because of the base and the acid. The acid is a strong acid. So the salt still has some acidic nature. So this can still be considered an H plus source. So you learn all of that type of stuff in Gen Chem. And we actually, when you did the nitro reduction, if you use zinc, what was the proton source in lab? Who used zinc in lab? What was your proton source?
It's all used sulfonic acid.
No, that was azonium. Ammonium chloride, yes, thank you. So, zinc ammonium chloride? Oh, it can't be a proton source. So, since we have a proton source, I'm just going to go ahead and protate this, okay? Well, I'm not going to do full mechanism because until a point. We have ammonia. We've got H plus. That comes from here. First thing is, what do you get when aldehyde and ammonia react? You get imine, right? Aldehyde ketone, amine, imine. All right? This was 2 pages ago. We reacted it with ammonia. If you did this mechanism, you can use an H plus catalyst in your mechanism because it can come from that. You get the imine. Now, I don't know that we've ever added anything to imines, nucleophiles. Now you can add water to there, and you can go backwards. But have we added anything else? Basically, we have cyanide, okay? And from here, we're going to get this product. Now, mechanistically here, cyanide adds here electrons up, just like if this was a carbonyl. Okay? If under my hand was an oxygen, we would add electrons up to oxygen. We can also do this with imine. And just about any chemistry we've ever done with carbonyls, you can do the same thing with the double bond N. It's not quite as reactive because the nitrogen is not as electronegative as oxygen. But you can do this with acid catalyst or without. I'll do it without. This adds electrons up. Boom, boom. Cn, N, H. What do we have here? Yes, negative. That's just a nucleophilic addition to the imine. Now what do we need to do to get final product? This needs to pick up an H to go in H2. Well, you got that proton source around, ammonium chloride. You can pick it up, and then there you go. So it's basically a simple addition to an imine as opposed to a simple addition to a carbonyl. Again, we could have put the proton on first, made that positive, and then when we added, we would have gotten there directly. Really all depends on how acidic it really is. Okay, any questions about how you get to this right there? It's essentially addition of HCN to an imine. HCN. At that point though, the cyano, you can do standard hydrolysis of it. And we know we can hydrolyze the cyano group, which is an acid derivative, to what? Oxalic acid. Okay? Aqueous acid, you could also do aqueous base. But you hydrolyze your cyano group, and there you go. And you have at the end a alpha amino acid. And this process is called the Strecker amino acid synthesis. It does have a name to it, as in a person's name. Probably one of the least common of those that do have names. I'm not going to say this is one of the top 10 reactions in organic chemistry. It's probably one of the top 10 synthesis reactions in biochemistry. Any questions about that? Of course, you can, amino acids, this substituent here varies. That's how you have variable amino acids. Of course, this here can vary. I mean, you can have any aldehyde you want. That's just your starting material. Questions? So, as practice, you can give a synthesis of leucine using the Strecker amino acid synthesis. Okay? We can look at that next time. Reductive amination. Now, although this does not have a proper name associated with it, this is one of the top 10 reactions in organic chemistry. Reductive amination. I say it's a great way to indirectly add alkyl groups to amines. Let me introduce you to this. First is reaction. You start with an aldehyde or ketone. Reacting with an amine. Here I'm doing a primary amine. Product would be imine, right? Again, all these A, B, C, D, and E falls under imines. Okay, we see imines as intermediate. Well, the imine, this double bond can be reduced. Just like carbonyl. I mean, if you have this, can't we add an H here and H here and get H here and H here? Now it looks funny with these H's drawn in. That's just a reduction of that to the alcohol, right? Well, don't look over there. What would you use to do this? Somebody said one reactant. There you go, final exam. What would you use to do that? LAH or sodium borohydride, right? After class, go back. You remember we did the redox cycle with estrogen and went from estrone to estradiol? Okay, please review this. All right, H minus, boom, electrons up. There's now two H's there, electrons up to give O minus. What do we have to do to put the H on? H plus workup. Some type of H plus workup or a protic solvent. Okay? All right? You guys seem to forget so quickly. That right there is standard carbonyl chemistry, that is like ABC. Alright, well the same thing can be done here. Sodium hydride, H minus, boom, remember? Just like we did before, I said the imine, you can do all these reactions with the imines. They're not quite as reactive. Electrons up, boom, there's one H, there's now two. This becomes minus with an R. What do we need to do to get that product? H plus workup. Now it may look odd because I drew the nitrogen that way instead of up, but it's CH2. It's CH2, right? NHR. Okay? If you think mechanistically, it doesn't matter how you draw the product. So it's just like you can also use hydrogen plated on carbon, just like an alkene. Now hydrogen doesn't work well with carbonyls. I'm not quite sure why. It works better when there's a ring next door. But usually if there's a benzene ring next door, it completely cleaves the oxygen off. It works a lot better with imines, just to give basically, boom, two H's. And of course when we're using this, we're not even doing an ionic mechanism. It's more like, okay, here's the pi bond and boom, two H's come in from the catalyst. Right? We never really showed ionic mechanism for that. So, what's the overall process? This nitrogen has how many R groups or alkyl groups? One. How many alkyl groups does the nitrogen have now? Two. Because this over here is another alkyl or R group. It's a benzyl.
So does that first step not require an active catalyst for a hydroxyl catalyst? Not the reduction part of it, I'm talking about the formation of the imine here.
No, it doesn't. And we've actually said that a couple of times. For example, in the Wolff-Kishner, which was under basic conditions, we also made an imine.
No catalyst.
Right, we were under basic conditions. You don't have H plus catalyst under basic conditions. Also, when you made the imine in lab, you didn't use an acid catalyst. So, a great way to indirectly add alkyl groups to amine. That's essentially what we did here. Now the amine is not the starting material over here, it's actually on the line. That doesn't matter. They're both key reagents. You could put the amine here and you could put the aldehyde on the line. That should not throw you. Alternatively, we've essentially put a benzyl on the nitrogen. Tell me another way to put a benzyl on that nitrogen. Grignard with a film?
What you said, put
Yeah, the
benzene on the nitrogen, is that what you asked?
Benzyl.
Benzyl on the
Yeah. How would you make this another way, starting with this amine? We need to put the circled group on the nitrogen, right? Tell me another way to do it. It would not be Grignard. Grignard's a nucleophile. I mean, if you want to take a benzyl Grignard, right? That's essentially this, right? How's this going to react with that?
It won't.
You might take an H and make toluene,
Could you get that?
but there's no way this is going to become bonded to the nitrogen. I mean, the nitrogen has a lone pair. Basically, if the nitrogen bonds to that carbon, you got two extra electrons there.
That's
This is
okay.
Gallic acid.
Oh, this is good leave. On the card.
Now we need a leaving group here,
Yeah.
where this lone pair can come in here and kick it off. And this would be SN2, and that would be a direct alkylation of the nitrogen. But there's problems with direct alkylation. What's the problem with direct alkylation? Polyalkylation, because once you get your product, then this here can go react again and put a second benzyl on. The great power of this indirect approach is you don't have polyalkylation. You put just one group on. And actually, if you go back to the SN2 handout in Organic 1, when we looked at nitrogen being a nucleophile, it briefly discussed the problem of direct alkylation. I showed you an alternative where we used azide, and I told you in Organic 2 we would see other ways to indirectly do that.
Didn't we have one where, with a phthalic acid?
Gabriel synthesis. It was phthalimid. Yes, look back at the Gabriel synthesis is another indirect way to put alkyl groups on nitrogen. Yes? The reductive amination is probably the most important or common way of all of them. Essentially, this is your electrophilic source, but it gives the double bond. You then have to reduce the double bond to get your product. Okay, let's practice here. Can you do this all together? And when I introduced it, I sort of showed making the imine and then doing that. Two totally different steps. You can make the imine 1 week and then isolate it, purify it, and then turn around and do that. And actually, didn't we do that in lab? Didn't you make an imine in lab and then didn't you reduce it?
Yeah.
Yeah, you did that. You did it a two-step process. You can also do the whole thing in one step, where everything is just combined and both things happen in the same flask. And that's actually more common. But you don't have the fun of isolating the imine. For example, here is it all combined. Methylamine reacts with the aldehyde to give what? Imine, right? And then what will hydrogen in the presence of a precious metal catalyst do to this double bond? It'll, like an alkene, H here, H here. When you do that, you get that product. So you can mix all the reagents together. And this will be a classical reductive amination sequence, with the imine being the key intermediate. Where it is, you would put this in brackets, which means that this is not isolated, but it's a key thing that's formed along the way. Okay. What about this down here? Can we use methylamine and maybe sodium borohydride together? First off, you got to know quickly that that would be the proposed product. What's the intermediate? Imine with double bond. Then you just reduce the double bond. So you got to be able to show the product. That works. This has big problems. What's the problem here? The problem here is that sodium borohydride will reduce this, and you will get you'll just get reduction of your ketone. Or it will be a major byproduct. You see, hydrogen, like I said earlier, remember, doesn't reduce carbonyls that well. And so it won't reduce your carbonyl, you'll just get imine formation. But the imine for some reason, is more susceptible to reduction with hydrogen. But if you try to do this, it won't work because sodium borohydride will reduce your ketone. Well, chemists are always up for a challenge, and there is a hydride reagent that will not do this or cause this problem, and it's a new reagent for us. Sodium cyanoborohydride, if you use that, it works because sodium cyanoborohydride will not typically reduce a carbonyl. Sodium cyanoborohydride, first off, sodium is plus, so that means all this is minus. Well, what's minus? Boron's minus, sodium plus. Basically, it's where one of the H's is replaced with a cyano of sodium borohydride. Now, does the cyano make this a stronger hydride source or weaker than? Very good, weaker. Cyano is withdrawer. If it's a withdrawer, there's less minus on the boron. If there's less minus on the boron, it's not as eager to shoot off those H minuses. Right? So it's weaker. For that reason, it apparently does not reduce carbonyls that well. But it still will reduce the imine. And so, this reagent here is very popular for reductive amination because of its selectivity. And it's classical reductive amination using sodium cyanoborohydride, which is the only place you're going to see this reagent. Okay, so predict products. You guys on my left do the first one, you guys on my right do the second one. We'll all do the third one. You need to be able to recognize when you see this, hey, this is like a reductive amination sequence. Then I would recommend drawing what's the key intermediate? The imine, or imine, or shift base, whatever you want to call it. And then after you draw it, go from the double bond, put two H's on it to give you your single bond, which is going to be your end product. This is just generic for reduction, right? Of course, there's two H's here, right? I just like to draw the H in of these things that look like aldehydes to me. Just because I drew the H in there doesn't mean it's not here. There's two here. You always draw H's on heteroatoms, right? So there's two new H's here, one there, one there. There's your product. You can draw it however you like. But the nitrogen now has two alkyl groups, where at the beginning it only had one. So we put an extra alkyl group on our nitrogen. How do we do? Questions? Product down here. I'll just draw the final product. Where the intermediate was the imine, where you had double bond between nitrogen and carbon, right? That look right? Okay, the one below I'll let you do on your own. What's going on down there that we need to recognize? Yeah, intramolecular. Okay? Show the product down there. Okay. A minute or two, let me set us up for next time. We didn't get to the Wittig. Wittig reaction, we'll be looking at the Wittig. There's written material in the other handout. I think I have the mechanism shown, etc. Before we get there, though, we're going to synthesize methamphetamine. Okay? Here's the question. Please do this for next time. We'll look at it quickly at the beginning of class. Provided two different syntheses of meth. Both of them using a reductive amination sequence. Two different reductive amination sequences to make methamphetamine. Do we need to turn this in as homework? No. You're going to do it on your own, and we're going to look at it on Friday?
Yeah.
Okay. See you in lab this week. Remember, you got to have a group name and a aldehyde choice.